we are going to derive the electric field for some point above a linear charge distribution. So here's my image. I've got a linear charge distribution, happens to be positive. I've got a dot, distance r away, and the dot is dead center, yay symmetry. And so we're going to go from negative a to a. So let's see, how do we derive this sucker? So how do we get the E field? Well, step one is we have to look at all of our pieces. So here we have a piece of charge dx, but we also have, sorry, dq, it's a piece of charge, but we also have a little piece of the length, so it's dx as well. Now, since it is a linear charge density, that would be charge per unit length. It's the same ratio as a piece of charge during a piece of length. I'm just going to call that dx. Now, if we look at what this guy is doing, it's going to create an electric field, but it's just going to be a piece of the whole because that's the piece of the entirety of the field. Now, this piece is at an angle. So I have myself a y piece and I have myself an x piece. And the angle between them, we'll call that theta, which is the same theta here. So beauty of symmetry is that I do not care about the x part, I only care about the y part. So let's get this party started. Step one, we draw our image, we kind of broke it down, got all set up. Step two is we want to collect all the pieces together. So let's look at what are all the pieces that we have at our disposal. So one thing we know is that the total electric field is equal to the integral of the piece. Now the piece in this case is just the y piece. So that's the first little piece of our puzzle. Second little piece is that dEy is equal to dE cosine of theta. We also have dE is equal to k q dq over r. Let's do some erasing here. I don't like that. Is equal to k dq over, in this case, let's call this b, length b squared. And that's from Coulomb's law, which says the electric field at some distance away is kq over r squared. Well, r in this case is our b value, and since just a piece of the field, it's just a piece of the charge. We also have the fact that cosine of theta is equal to the adjacent, which in this case can be r, over the hypotenuse, which is b. Well, b is equal to the square root of x squared plus r squared, because Pythagorean theorem. So we'll make that to the negative 1/2. I don't like square roots. X squared plus r squared to the 1/2. All right, so those are all little pieces. Now we're going to combine all these pieces together and just do a whole bunch of replacement. So that's going to give us E is equal to the integral of k lambda dx. And you're like, where'd the lambda dx come from? That came from over here. I skipped another piece. I skipped a piece of the puzzle. We also know that dq is equal to lambda dx, and that comes from here, that relationship. All right, back on track. So that over x squared plus r squared, because you would have to square that, times cosine of theta, but cosine of theta can be replaced with something else. And that can be replaced with that whole r over x squared plus r squared to the 1/2. That's what we're going to start with. Now, I want to take a moment and pause, because a lot of people say Okay, Szymanski, how do I know, like, do I get into angles or degrees? Because if we look, we've got a theta here, and we've got some r's over here as well, right? So how do we know if we're going to work in angles or if we're going to work in distances? So here's my advice. If you ever have like a point and it has to do with some sort of inscribed within an arc, it's inside the arc, then you do theta. But if you ever have some point and it's away from some flat surface, then you want distances. And when I say flat surface, it could also be a ring because that's a flat surface. So I would also want to use R. Okay. Could be a disk. That would also be a flat surface. So that would be R. So if it's inside something that has some sort of arch to it, then use the angle. If it's not, you want to get into R's. Just my personal opinion, personal advice. Take it, leave it. It's up to you. At the end of the day, you'll get the same answer. Just I find this to be a little more agreeable to my liking to a certain point because then I can it's more uniform, I guess. That's probably the way to put it. Because the either way, the calculus is not my friend. All right. So speaking of the calculus, when we go to combine all this stuff, we get E is equal to the integral, and we'd integrate from a to negative a, because that's what we defined, a to negative a, of k lambda r dx over r squared, nope, x squared, x squared, x squared, x squared plus r squared to the 3/2. Now, I'm going to pull out the constants. So k is a constant, lambda is a constant. The r is a constant because it's always going to be the same distance above the surface. So now I'm going to then look at, well, what's actually going on here. So then I've got between a and negative a, and all that's left is dx over x squared plus r squared to the 3/2. All right, now, how do I derive this? Well, that's up to you, but in all honesty, I use an integration table. All right. So if you use an integration table, basically you look it up, say, okay, what's the derivative of dx over the stuff inside of an integral? Probably be like a's and b's and stuff. Then you get your output, which is e equals 2k lambda x. Whoops, not x, Mansky. Because now I've got a's. Boop. A over the quantity r to the a squared plus r squared over the 1/2. And that would be the equation for the electric field. And then if you're wondering, but okay, well, hold on. How do I get there? Remember, when you're doing the AP exam questions, all the work above is worth the majority of the points. The actual answer is basically always worth 1 of the 15 points. So you want to make sure that you have it set up. And if you have it set up and you're like, ugh, that calculus looks ugly, you just write, use calculus to solve for E, smiley face, walk away, do the next problem. All right, you'll still get a 14 out of 15 if you know what you're doing. So at the end of the day, the calculus is not worth all that much. All right, so hopefully that helped with understanding how to derive electric field at some point away from a linear charge distribution. You guys have a great day. See ya.